Hi all, thank you for tuning into my channel on ozone technology course. This is session 15A and it will be involved in the principles of ozone gas transfer to either water or a fluid. This session introduces some basic principles of gas to liquid transfer. It is very important to know the basic requirements as the success or failure in any applications depend upon the fundamental knowledge of the principles. The principles help us understand the issues of gas to liquid transfer in ozone applications. The factors affecting the gas to liquid transfer are solubility. If the gas is very soluble in that liquid, then there's more of the gas that will move into the liquid. If the polarity of the gas in an anhydrous form, virtually non-polar, will have no effect. But if it is with a bit of moisture and the liquid is polar, then more gas will transfer into the liquid. The concentration of the gas also becomes an important factor. So if you try to pass a gas at high concentration into the liquid, more of the gas will transfer into the liquid because the partial pressure is very high. The differential in partial pressures between the gas and the liquid. So if you find that the partial pressure of the gas is higher in the gas than the same gas in the liquid, there will be a flow of the gas into the liquid until both the partial pressure of the gas in the vapor form and the gas in the liquid form will be is equalized. The pressure of the liquid. So if you apply high pressure of the gas into the liquid, there will be more of the gas that can flow into the liquid. Therefore, it will be useful to try to apply high pressure onto the liquid. However, with respect to ozone, we have an issue because if you try to compress the ozone, it might just convert back to oxygen. So we have to be very careful as to how far we can compress the ozone so that we can try to put more ozone into the liquid. Now, if the temperature is high, then less ozone will go into the fluid because the solubility of a gas in a liquid depends on the temperature. The higher the temperature, the lower the solubility, and vice versa. Flow rate is important. Lower the flow rate, the higher contact time, and therefore the more of the gas can flow into the liquid subject to its reaching the equilibrium. So you cannot just make it extremely slow flow because once it reaches the equilibrium at a particular time, then if the flow rate is so slow that it will be a waste of your efficiency. So we have to get an optimum flow rate so that the maximum of the gas can dissolve in that particular time. If the reactability of the gas is very high, then it will also react, it will also flow into the gas, but this will not apply with the ozone unless, of course, ozone is used as a chemical to react in the chemical reactions. The pH of the liquid also will not will be useful because if the pH is very high, ozone can be converted and is transferred immediately to free radicals, and ozone can flow into the system. I am considering some legal laws of physics which will be applicable in our transfer of ozone to the water. However, we need not know the exact principles, except that understand certain things can happen. So the laws that are applied are Raoult's law, Dalton's law, Henry's law, the Gibbs phase rule, and Antoine's equation. We have to know some information about partial pressures before we go into the law of gases. Both liquids and gases are known as fluids, and the law of gases will apply as it will to be the law of liquids. So when 1 mole or molecular weight of water turns to vapor or gas at 100 degrees centigrade, the vapor pressure will be 1 atmosphere, that is 760 millimeter or 30 of water or 30 millimeter of mercury. If half of the water is evaporated in a closed container, the partial pressure of that vapor will be 380 millimeter of water or 15 millimeter mercury. Hence, the quantity of water that remains as vapor depends upon the partial pressure in the vapor phase. When there are two fluids of unequal solubility with each other, either liquid-liquid or gas-liquid, the amount of gas that will flow into each other or the amount of liquid that will flow into each other depends upon the partial pressures of the gas or liquid in each of the fluids at that temperature and pressure. Each fluid will exert its own partial pressures at that temperature. That it will be depend on the boiling point of that particular fluid or liquid. Raoult's law states that the partial pressure of each component of an ideal mixture of liquids is equal to the vapor pressure of the pure component multiplied by the mole fraction in the mixture. In consequence, the relative lowering of the vapor pressure of a dilute solution of a non-volatile solid is equal to the mole fraction. Mathematically, partial pressure of the solution equals to X, that is a constant of the solvent, times partial pressure of the solvent, where P is the partial pressure of the gas mixture above the solution, X is the mole fraction, which is a constant, which is specific for that solvent. Where two volatile liquids A and B are mixed with each other to form a solution, the vapor phase consists of both components of the solution. The definition of mole fraction is the number of molecules of the substance compared to the total mole of the matter present. 1 mole is 1 molecular weight of gas. Dalton's law says the total pressure in an equilibrium is the sum total of pressures of the two gases, so long as the gases do not react with each other, i.e., partial pressure multiplied by the mole fraction equals to total pressure, P. Example, 0.25 mole gas over 1.0 total moles equals to 0.25 mole fraction. The diffusion of the gas to the liquid in our application is controlled by Dalton's law, where P divided by K equals to concentration of the gas in the liquid, where the P is the partial pressure of the gas and K is the constant of the gas. I am certain many people are a bit perplexed or confused of this information, but may I say that it is just to give some understanding of the transfer of the gas into the liquid. And if you know these principles well, you can virtually calculate how much of the gas moves from one liquid or a gas to the other liquid or a gas, and we can apply accordingly or make changes accordingly. Otherwise, we'll just have to depend on what some people have done, some other scientists have done, and use those applications and work on it if you're not well versed with such chemical principles. Now, if you want to determine the vapor pressure of any gas or liquid, obviously now there's the Antoine equation is used. That is log 10 of P equals to A minus T plus C, A minus B over T plus C, where P is the partial pressure, A is the constant for the gas to liquid, T is the temperature, and C is the concentration. If you have book of chemical constants or standards, you will be able to find from there, which is the constant for the gas or the liquid, A. It is found, it's a standard. This book is a standard of constants for various metals, gases, etc. The Henry's law of diffusion of gases is the amount of gas dissolved in the liquid is proportional to its partial pressure above the liquid. It's quite obvious, as we did say, because the higher the partial pressure above the liquid, the greater the movement of the gas into the liquid. Therefore, if you know the partial pressure of the liquid and there's no gas in the partial pressure of the gas, let us say the partial pressure of the gas, and if you know there is no gas in that liquid, you can identify or calculate how much of gas will go into the liquid. So that is how you be able to measure how much of ozone can go into the liquid. Again, as I did mention, in most practical applications, we do not have to consider this because most of that, once you transfer, you can measure the amount of the gas in the liquid and you continue until you achieve the maximum and then you stop. This way we were able to, instead of calculating theoretically and applying, we can still manage to make the applications, do trial and error. The solubility of the gas in the liquid will be the transfer of the gas to the liquid. That will depend on the solubility of the gas in the liquid. The greater the solubility, the greater transfer. For example, ozone is more soluble in water than oxygen. So if there is 21% of oxygen in the water, the amount of ozone can be more than 20% or more than 21% of ozone. Water is polar, ozone is more polar than oxygen. Therefore, more ozone can dissolve in water compared to the oxygen. The temperature, pressure, and solubility. The higher the temperature of the water, the lower solubility of the gas. So, preferably, we would like to apply the gas at as low temperature as possible. Because if you increase the temperature of the liquid, then less gas will be transferred. Flow rate. The contact time between the gas and the liquid depends on the contact time of the gas to the liquid. Hence, if the flow rate is very fast in the transfer of the gas to the liquid, the less the gas transfers into the liquid. If the flow rate is high, the amount of gas transferred is reduced because of the lower contact time. If the flow rate is low, obviously more gas will be transferred, but once the maximum transfer is achieved, then there's no purpose of reducing the flow rate or keeping the flow rate at that level. Therefore, we must come to an optimum flow rate where 100% of the gas that can transfer into the water at that temperature or pressure will be in it, will flow into the liquid. The next is reactability. The transfer of gas will be greater if the gas reacts with the solution. This will not apply to us because we are dealing with ozone that does not react with water. pH is also an important factor, but we don't necessarily have this issue when we transfer ozone to the water. As I did mention to you, with respect to the pH, polarity and pH are related. So if the pH increases the polarity, and because ozone is also polar, the solubility can increase. But if the pH is above 8, then ozone will activate the formation of free radicals that will not show up in the redox potential. The effect of polarity of the solvent on ozone. Ozone is a polar molecule, and therefore the greater the polarity of the solvent, the greater absorption or solubility of ozone. Pure water has no polarity and it does not conduct electricity. But if a minute presence of inorganics, such as traces of chloride ions or other ions, the solvent becomes polar and the solubility of ozone in the polar solvent increases. In order to increase its ozone absorption, it may be useful to increase the polarity of the solvent, subject to its interference in the reaction or resulting application of the solution. For example, ozone dissolves more in saline than normal water, and treatment of swimming pool water or salt water, chlorination for residual, chlorine is reinforced and enhanced. So as I said, ozone, there will be more ozone if you apply ozone in the swimming pool water, which is chlorinated and salt water. In conclusion, we must take into consideration the physical properties of gas to liquid transfer in identifying the precise procedure to be applied when we use ozone for various applications. Knowledge of these principles will assist us in the correct and optimal application of ozone and increase the efficiency and reduce the cost of the application. We have come to the end of this session, session 15A. Thank you for having the patience to listen to the session. The next session, 15B, will be on ozone application in potable water. If you are new to this session, please refer to sessions 1 and 2 on the program course details and sessions 3 to 14. If you like this presentation, I would appreciate if you please click the like icon and subscribe icon, and you will be informed of the uploading of the next session. Thank you once again and have a pleasant day.